Beats and Bacteria by Mayukh Kiran Datta. I am going to be growing bacteria with music. I hope you find this interesting. Background research. A German sewage plant located southwest of Berlin has recently started playing Mozart's composition to enhance bacterial growth. The bacteria grown in this sewage plant break down residual sludge, and with higher bacterial growth, the plant has a fewer sludge yield, saving the plant €1,000 per month. This process was developed by a small firm called Mundus. The head of that firm, Anton Stuckey, says Mozart's music has a very good harmony in correlation to its rhythm. The nearby farms also benefit from this process because the bacteria also break down sewage runoff which used to run off to these farms and destroy the crops. Background research continued. Stuckey claims that the pitch, vibration of the music, along with sufficient oxygen, enhances bacterial growth. Using this process, wastewater facilities will be able to save on energy costs and reduce residual sludge. A winemaker in Austria plays different kinds of music during the fermentation of wine. The winemaker believes that the vibration from the music increases yeast growth. This process speeds up the fermentation. As a result, the winemaker saves approximately €2,000 every month. Reasons for my experiments. There were a lot of experiments done to test the effect of music on the growth rate of bacteria. However, the researchers of these experiments tasted the effects of different kinds of music on the bacterial growth rate. And common sense tells us that bacteria cannot differentiate between the kinds of music. So I tested the effect of tempo and volume on bacterial growth rate. Question and hypothesis. Question: is bacterial growth affected by changes in tempo and volume? Hypothesis: if the pitch of a song affects bacterial growth, then exposing bacteria to changes in tempo, measured in BPM, and volume, measured in decibels, of the music will also result in changes in bacterial growth patterns. Materials used: 5 petri dishes, 1 bottle of agar solution 500 ml, 5 sterilized swabs, 4 music players with volume levels up to 100 decibels, 4 Sony headphones, 2 music playlists approximately 4.5 hours long, camera, ruler. Procedure. To prepare the petri dishes, I first microwaved the agar solution and poured the agar in the petri dishes. Then I let the agar cool down. I collected the bacterial samples from my computer's keyboard to control the type of bacteria, and then inoculated the petri dishes using sterilized cotton swabs. I also wanted to prove that different genres of music does not affect bacterial growth rate, so I had 2 playlists with varying genres of music. Playlist 1 had music whose tempo ranged from 150 to 180 BPM, and Playlist 2 had music whose tempo ranged from 50 to 90 BPM. The volume of the music was controlled remotely. Among the 5 petri dishes, petri dish 1 had no music played. Petri dish 1 was my control. Petri dish 2 had music from playlist 1. The volume of the playlist was set to 100 decibels. Petri dish 3 also had music from playlist 1. The volume of the playlist was set to 30 decibels. Petri dish 4 had music from playlist 2. The volume of the playlist was set to 100 decibels. Petri dish 5 also had music from playlist 2. The volume of the playlist was set to 30 decibels. Procedure continued. I placed 4 headphones on the petri dishes 2, 3, 4, and 5 respectively. Petri dish 1 was the control. No music was played for petri dish 1. The petri dishes were placed in a warm, undisturbed environment, and the music was played for 5 days. The bacterial colonies were counted every 24 hours. The bacterial colonies could be counted for the first 3 days. On the fourth and fifth day, the colonies were too mixed to be counted, so I counted the colonies using the grid system. In the grid method, I drew a grid on the surface of an empty petri dish. I placed that empty petri dish on top of my samples, and I counted every box that a bacterial colony inhibited. Results. Day 1. Petri dish 1, 10 colonies were visible. Petri dish 2, no visible colonies. Petri dish 3, 15 visible colonies. Petri dish 4, 13 visible colonies. Petri dish 5, 7 visible colonies. Results. Day 2. Petri dish 1, 20 colonies. Petri dish 2, 7 colonies. Petri dish 3, 28 colonies. Petri dish 4, 27 colonies. Petri dish 5, 35 colonies. Results. Day 3. Petri dish 1, 43 colonies. Petri dish 2, 12 colonies. Petri dish 3, 50 colonies. Petri dish 4, 41 colonies. Petri dish 5, 60 colonies. Results. Day 4. The colonies were too mixed to count, so I used the grid system. Petri dish 1. Colonies inhibited 41 boxes. Petri dish 2. Colonies inhibited 25 boxes. Petri dish 3. Colonies inhibited 64 boxes. Petri dish 4. Colonies inhibited 70 boxes. Petri dish 5. Colonies inhibited 86 boxes. Results. Day 5. The colonies were too mixed to count, so I used the grid system. Petri dish 1. Colonies inhibited 63 boxes. Petri dish 2. Colonies inhibited 40 boxes. Petri dish 3. Colonies inhibited 90 boxes. Petri dish 4. Colonies inhibited 60 boxes. Petri dish 5. Colonies inhibited 114 boxes. Observations based on the results. The change in volume greatly affected the growth rate. This claim is supported by results of Petri dish 3 and 5, which was exposed to low volume of 30 decibels and had more colonies than Petri dish 2 and 4, which had volumes of 100 decibels. The decrease in tempo did have some effect. Petri dish 3, which was exposed to slow tempo and high volume, had more colonies than Petri dish 2, which is exposed to high volume and fast tempo. 1 millimeter of bacterial colony has approximately 100 million bacterial cells. Given that fact, in the fifth petri dish, the longest bacterial colony was 4.5 cm long and 1 cm wide. However, in the second petri dish, the shortest colony was 1 cm long and less than 0.5 cm wide. The rest of the petri dishes had cultures of 0.5 centimeter to 1 centimeter long and 1 centimeter to 0.5 centimeter wide. Observations based on the results continued. My hypothesis was supported by this experiment. The change in tempo and volume did affect the bacterial growth rate. Slower tempo and lower volume increase bacterial growth rate, but faster tempo and higher volume decrease bacterial growth rate. The biggest factor contributing towards bacterial growth rate was the change in volume. Conclusion. The tempo and volume of a song affects how much vibration the song produces. The lower the volume and slower the tempo, the lower the vibration of the song. Bacteria are perceptive towards the level of vibration in their environment, and the bacterial colonies responded better towards low volume and slow tempo. Under these terms, I conclude that bacteria grow faster if there is low vibration in their environment. Since my experiment had varying genres of music, I also conclude that the effect of the genres of music does not affect the bacterial growth rate. Questions for further study. What is going to be the bacterial growth rate if the vibration of the sound is above or below the human hearing threshold? What is going to be the bacterial growth rate if the music is excluded from the songs and only the bass is used? Are we going to get the same effects if we experiment with larger organisms, example insects? Sources page.